Right, for next up, we have Anschel Shaffer Cohen with us he'll be telling us about what does a typical infinite type surface look like. Please.
All right, thank you very much, Turbo. Thank you for inviting me. Infinite type. So here's the situation. I was very excited to be invited to do this. And then I thought, oh no, I haven't actually produced any new results worth discussing in kind of a while. So I decided instead to take the liberty of doing something that I'm probably not old enough to get away with, which is to give a talk in which I present only questions to which I don't know the answer. Also, I should say, the way I have my computer set up right now, I can hear you, and please do interrupt if you want, but I cannot see chat. So if someone says something important in the chat, someone else should repeat it out loud. Cool, okay. So we've heard a few people talk about infinite type surfaces. I like infinite type surfaces a lot, and a lot of the statements that have been made about infinite type surfaces are, I think, they're lacking an important piece of information. And here's what I mean by that, right? When I say, for instance, in the finite type case, when I say that the fundamental group of a surface is hyperbolic, like almost always. Right? What I mean by this almost always is, well, there's finitely many exceptions. And because there's infinitely many finite type surfaces, finitely many exceptions is something we can sort of like, okay, we'll deal with those individually. That's just some little edge corner case and everything else is good. And for infinite type surfaces, this is fine because the fundamental groups are all free. But as soon as we get to many other statements that are made about infinite type surfaces, we have a problem. And the reason we have a problem is that there's too many infinite type surfaces. Okay, so if I give you some property that we might care about an infinite type surface, I'll start with a simple one. How about genus, right? So there's a bunch of results that have been proved for surfaces that have certain genus properties, right? So like, there are many results in big mapping class groups that are about surfaces with zero genus. Or surfaces with every end accumulated by genus. For instance, the result of, this is not one I made a note and I'm terrible at remembering the people, it's Patel, Vlamis, maybe also Armayona, right? These surfaces have the property that the pure mapping class group of a surface is precisely the closure of the compactly supported. Right, this is all the mapping classes that fix the ends. And this is all the mapping classes that have compact support. All the mapping classes that have a representative which has compact support. Right, this is a topological group. You take the closure of those and that gives you everything it possibly could. Right? Which is a cool result. And this is precisely true for surfaces. Oh no, it's not with zero genus, it's surfaces with at most one end accumulated by genus. But then the question becomes, okay, but how many surfaces have at most one end accumulated by genus, right? If I reach my hand into the bag of surfaces, how likely am I to get one that fits this criteria? And this is, so to me, this result leads naturally to that question, right? The result says that all these things have this property. It leads to another question. There's a few others like that, but there's a couple that are even more worrying in some ways. Hannah brought this up in her talk, right? Which is like, Man and Rafi introduced this notion of a tame end space. And I'm not going to define this right now in detail, but basically it means that if you look at not all the ends, but at least the important ends, the ones that matter for their constructions, their topology is reasonable. They all sort of are locally self-similar. The closer you get to that end, the more you keep seeing the same thing over and over again, right? And their results about which big mapping class groups are CB generated assume tame end space. Okay, and so and they have a sort of justification. I should say, if it's not obvious, I'm not throwing shade. This is an amazing paper, and it's the basis of most of what I've done in the last several years. But I do think there's this awkwardness, right? What is the justification of this? Well, they say if the end space is countable, then it is tame. So all the countable end spaces are tame. We only get the problem with the uncountable ones. Right, and it's worth noticing that there exist, right, there are uncountably many distinct infinite type surfaces. And uncountably many of them have countably many ends, and uncountably many of them have uncountably many ends, right? So this set of countably many ends, which is a perfectly reasonable thing to want to sometimes restrict your attention to, it's among other things, it's much easier to understand, right? This is uncountable, and so is its complement. So we can't do the sort of, well, there's finitely many things for most of these problems. There's a few exceptions, right? There's some surfaces with one end. Okay, there's only two of them. But once things get big, you have an immediate problem. And the other justification is that every surface that anyone's ever thought of in any published work is tame, right? Except Mann and Rafi when they were searching for a counterexample. Anyone has cared about. But again, that's sort of suggesting maybe that we're just really bad at looking, right? Maybe the surfaces with tame end space are like the computable numbers or something like that, in that, yeah, there's lots of them, but actually, really, most surfaces don't have this property, right? And Hannah mentioned that people call this a mild condition. I've been guilty of calling it a technical condition, right? But what we really mean by that is we don't have a justification for it. It's necessary for these proofs, and we haven't figured out what other things, we haven't figured out how common or uncommon it is. So I'm just going to mention a few other properties that we might want to know how common or uncommon they are, right? So from Mann and Rafi, we have tameness, we have non-displaceable subsurfaces, right? A lot of their arguments depend on whether or not a surface has one of these. A non-displaceable subsurface is sort of what it sounds like. It's a finite type surface somewhere in your manifold that you can't, by homeomorphism, move it totally off of itself. We can ask about self-similar n spaces, which I think Elizabeth talked about a bunch. We can also think about telescoping n spaces, which is another thing that's sort of like self-similar, but there's two of them. Right, there's other people have determined under what circumstances. So Horpez, Ching, and Rafi have said when the mapping class group acts in an interesting way on a hyperbolic space. That's a Gromov hyperbolic. They classified those, right? And they classified them up to tameness. They classified them in a very satisfying way. It's a lovely result. And it turns out to be very close to this non-displaceable subsurface thing. And again, it's like, okay, but how likely is that, right? Like, what are most of these like? And periodic homeomorphisms, doubly pointed. I'll toot my own horn for a second, right? I wrote a thing about what I call translatable surfaces. These are basically surfaces that have a nice action on a kind of curve graph. Again, okay, but is that most of them? Is that none of them? Likewise, some of these mapping class groups are actually themselves on the nose delta hyperbolic, which is really cool. Which ones? There is not yet a complete classification of those. I've heard people claim that they're close to one, but a while ago. But we found a few, and there's probably more, but like how many? Okay, so there's the problem. Okay, hopefully I've convinced you that there's a bunch of interesting questions here that should be answered, right? And so how do we go about answering this kind of question? Well, the program, which is basically Gromov, who asked this question about groups, and being Gromov, he meant finitely generated groups. He said, well, what does a typical group look like? And his solution was produce some probabilistic models. Okay, so there's two ideas here, right? You could either have some kind of probability measure on the set of all possible surfaces. But if you're not a probabilist, probability measures are like terrifying and weird. So another option is to come up with some idea of complexity so that there's a manageable number of surfaces at each complexity, and then let complexity get really big, right? So you come up with a probability measure on surfaces of complexity, less than n, and you let n go to infinity. Unlike in the finitely generated groups case, again, we have to deal with uncountability at a deep level, right? So this n is going to be like an ordinal or something, or these sets are going to be themselves uncountable. And then you ask questions, right? You say, okay, in this case, what is the probability of this happening? So my main point that I want to get across is we should do this. People who are interested in this should talk to me. We should come up with a way to define these so that we can and see what kinds of questions we can ask about them. One thing that's worth pointing out is so you could define a random surface sort of from the top, right? So the end space of a surface has to be a closed subset of a Cantor set, right? So you could try to find, all right, so here's an idea. Random closed subset of a Cantor set. I don't know how to do that. As far as I can tell, that isn't a thing that someone else has already done, right? But that would definitely give you something. There's an interesting problem that comes up here that I will get to momentarily, right? You could also, right, I've been saying random and probability, but bare category is also like a reasonable proxy for something being generic. So instead of a probability measure, maybe you could put a topology on the space of all of these things. That might also produce like results that people find satisfying. But another idea is, what if instead of trying to generate a random surface, we remember Hannah's talk and we try to generate a random graph, okay? Remembering that there's this natural equivalence between the two, right? So we want a random graph, and you think, oh great, random graph, that's like a thing that lots of people have studied. But you're wrong, because we want a random infinite but finite valence graph. Right, and then there's a very nice correspondence that Hannah talked about between these and infinite type surfaces, if we can make one. So I now want to present at least one idea that doesn't, two ideas that don't work, to convince you that this problem isn't completely trivial, or at least that I am not able to render it completely trivial. One is, I talked to a probabilist, a discrete probability friend of mine, Marcus Michelin, and I asked him, hey, if I wanted to generate like a random infinite tree thing, what would I do? And he said, oh, there's a standard thing, right? At each node, and I couldn't find the reference for this, right? At each node, you have, two possible children, and they exist with probability p, and then you do this process forever, and you end up with, for a given p, you end up with a probability measure on the space of possible graphs you could get. And you could also, like, you could add to this, you could like put in a loop at each node with probability q, right? And then at least represented in your probability space is every possible random graph, right? And the problem is that with probability 1, so basically always, this resulting tree has, or graph if you put it in the loops, has no isolated ends, right? Which means its end space is a Cantor set, which means at least in the loop-free version of this, it's not the full Cantor set, right? It's a different Cantor set that is a subset of the full Cantor set that you'd get if P was 1, if you had every branch, but it's still a Cantor set. So up to homeomorphism, we just have the sphere minus a Cantor set. So here's a nice random model that always produces the same surface, right? Which is deeply unsatisfying. Likewise, one source of infinite finite valence graphs is Cayley graphs, right? What if we take the Cayley graph of a random group. And then we could leverage everything we know about random groups. Someone immediately see the problem here? Right, the issue is that there's this great result about ends of groups, that there's always 1, 2, or infinitely many. And it's not hard to convince yourself that the infinitely many is a Cantor set. Right, so again, our end space is always 1 point, 2 points, or a Cantor set. And genus either goes to all of those ends or none of them, right? Somehow the amount of symmetry you get from your graph being a Cayley graph is too symmetrical. It makes it no longer possible to have interesting topology. So the question is there a nice model for this? Nice in the sense that it's aesthetically satisfying. And so when you say, aha, I've shown that most surfaces are tame, people will agree that you've actually used the word most correctly. Is there a nice model that doesn't always give the same few surfaces? Yeah, that's basically the end of my talk. But again, it comes with a plea: get in touch. If you watch this and you thought, oh, that's a cool problem, or if you watch this and thought, oh, this guy's an idiot, there's an obvious way to do this. Get in touch. Tell me what the obvious way to do this is, or tell me you'd like to work on this together, because I think there's a lot of interesting questions here. I made a much longer list of properties you could study that I realized as I was doing this was kind of a waste of time to write them all down here, but there's a lot there. There's a lot of open questions there's a lot of questions that can be asked that are obviously interesting, which seems great. All right, thank you very much.
All right, let's thank the speaker. And any questions? So I do have a question. So for random groups, one way to study them is via the space of marked groups, which is really you put a topology on all the groups. And then you say generic behavior is something that happens, say open densely often.
Mm-hmm.
So is there a way to put a topology on the space of big surfaces, or?
Yeah. So what that comes down to is putting a topology on this guy, or at least that's a crucial part of it, right? Is can you put a topology on closed subsets of a Cantor set? Or if you like, can you put a topology on infinite, on whatever the topological, there's an intrinsic definition of this property. You need to be totally disconnected, compact. I'm probably missing one other adjective space.
Right. But here, can you not do something kind of stupid, which is you say the basic open sets are the things that contains a point in the Cantor set, and then you use that as a topology? Like, yeah.
I haven't thought about what the consequence of that is.
Because I think that's kind of what they do for space of marked groups, right? So
your basic open sets here are what?
So you pick a point in your Cantor set, right? Then
Okay.
One basic open set are all the closed subsets that contains this point.
Okay. That's not even a basis though, right? Like the intersection of two of those.
Yeah, so to make it a basis, you say for every two tuples in the Cantor set, you contain this tuple,
Yeah.
but don't contain that. That will be a basis. Finite tuples.
Mm-hmm. Yeah, I haven't thought about the consequences of that, but I will now. So thank you.
Okay. All right. Any other questions? I don't see any in the chat. In that case, let's thank the speaker again.